Alright, hello, my name is Brittany. This is my project for DS4100 for Spotify's Top Tracks of 2017. So the CRISP DM pipeline has 6 steps: business understanding, data preparation, modeling, evaluation, and deployment. So first, for business understanding, my dataset was the top tracks of 2017 Spotify playlist that has 100 tracks. I use the Spotify Web API to pull the different audio features for each of these tracks, and I wanted to investigate the data, determine correlations and trends, predict popularity of the track based on different features of the track, and really figure out what makes these tracks so popular. So for data acquisition, first I used the Spotify ARP package to easily access Spotify's Web API, so I extracted the audio features of each track of the playlist. And then to be safe, I also wrote that data frame to a CSV and pulled that CSV back into a data frame. So for the sake of time, I'm going to run all the code for the first 2 steps of the CRISP DM pipeline here, because it might take a little bit. Pulled in the data, acquisition from file, etc., etc. You can see all the values being assigned here. We'll wait for this to finish up. Okay, I think it's good. Yep, so like I said, pulled from the Spotify ARP package from the Web API, wrote to CSV, pulled in CSV. I used for data exploration the glimpse function to take a look at the data, so we can see with a little more readability here in my R notebook that the glimpse function gives you the different observations, the variables, which is the column, so 100 tracks with 30 columns. Just gives you a glimpse of it right here. And then to do some cleaning and shaping, I removed the irrelevant columns from the data frame that I pulled in. So like playlist name, the URI, the URL for the tracks, the album artwork, etc. And then to kind of comb through the data a bit more, I used the mismap function from the Amelia package to find any missing values, and since this is a really clean data set, there were no missing values, so I was all set there. For normalization and standardization of features, I did a few things. I converted the duration of each track from milliseconds to seconds. I renamed some columns accordingly. I changed the loudness from negative to positive values, since quantitatively, the smaller the loudness the value, the louder a song is. And then for exploratory data plots, I pulled in the ggplot2 package to create a bunch of graphs for this cool data that I had. So for example, for the top artists of 2017, I made this cool graph that showed all the artists that had more than 2 tracks on the playlist, and you can see Post Malone, Kendrick Lamar, Drake are top 3. The keys of the songs, C# was apparently the most popular key, and a cool density plot for loudness here, and I classified all the different tempo, beats per minute, to their different tempo markings. So you can see Allegro and Andante are the most popular tempo classifications of 2017. I also made these histograms for several different audio features that I had in my data set, so you can see high danceability, mid to high energy, low speechiness, low acousticness, low liveness, and valence, which is kind of the mood of the song, is kind of all over the place. With each data plot above, I also detected outliers, and I considered outliers to be any value greater than 2 standard deviations from the mean. I know we usually say 3 standard deviations from the mean, but since this is such a small data set and it's only 100 tracks, I thought each track was important for the big picture, so I ended up not removing those outliers. For correlation and collinearity analysis, I pulled in the core plot package, which created this cool graph over here. You can see that speechiness and loudness are positively correlated with each other. There's valence, which is positively correlated with danceability and energy. Energy and loudness are very negatively correlated. And since I knew that energy, valence, and danceability were positively correlated. I kind of wanted to see that trend again, so I created this density plot to kind of depict that. And like I said before, for new derived features, I created another column in my dataset called tempo marking, where I used buckets of different beats per minute tempo values for to classify them into adagio, allegro, andante, etc. And for normalization of the data, I performed a min-max normalization on the columns that were not already scaled from 0 to 1. So this included track popularity, loudness, tempo, and duration. Okay, now on to data storage and retrieval. So I used the R-MySQL package, and I created a database called Top2017DB. And then I created two tables in that database called Top 2017 and Top 2017 Numeric, which had only the numeric values of the original dataset. So I can show that code running down here. Let's scroll down to above the models here. All right, so I wanted to connect to MySQL, which I did here, and then create the database, which I did here. Drop database if exists, create database, reconnect to the database with dbconnect, and create those tables, Top 2017 and Top 2017 Numeric. You can see that dblist table showed that it worked. Okay, then for the retrieval mechanism, I basically just retrieved those two tables from the database as well, Top 2017 and Top 2017 Numeric, and put them into data frames. So for complex joins, I didn't really have that complex data, but I wanted to group the data by something. So I grouped by popularity ranges as well as mode, key mode, time signature. But for popularity ranges, I kind of grouped them into buckets and created this ggplot as well. So you can see the different popularities for the tracks. For training and validation subsets, I decided to split the data in half. So training was 50% and validation was the other 50%. We can see that I did this over here. Set the seed so it's the same every time. And that usually works. Okay, for regression analysis, so I kind of wanted to use this because most of my data that I was depending on was quantitative. So it really helped you understand how the typical value of a dependent variable changes when one of the independent variables is adjusted and all others are held fixed. So from what I gathered from my data exploration, usually there's high danceability, low to mid loudness, low speechiness. All of these are features that I use to construct my models. So first, I did a multiple linear regression, which is basically creating a slope y equals mx plus b line, and I used the LM function. And just for readability's sake, we can go to our notebook where I did this. So I used the LM function, and then you can see that the p-values I got weren't really significant, and I did this model twice. I did forward fitting and backwards fitting, and most of the time, the track popularity when I set the values to be what I thought created a popular track was the track popularity was high and the track popularity was low for the values I thought would make a not popular track. The next one I did was logistic regression. This was using the GLM function, which was similar. I did forwards and backwards fitting as well, and the p-values were also not very significant. And in addition, I did recursive partitioning and regression trees using the rpart function, which created this cool decision tree you see to the right. So my evaluation is basically that I was using track popularity as my independent variable, and none of the models I really constructed had any values that were less than 0.05, which is unfortunate, but for each type of model, I constructed 2 models with 2 predictions for each, so 4 predictions per type of model. I use these 2 formulas, so one with most of the numeric features and the second one with only 4 of the features to try to tune the model a bit. And overall, none of the p-values I really got were less than 0.05, but the model that was closest to being significant was the multiple linear regression model based on the only 4 variables: danceability, speechiness, acousticness, and liveness, and the p-value of that model was 0.57. So I'm running out of time, but for the future work, I would say more prediction models, a larger data set to work with, and further data exploration. You can find my project available on GitHub. I will provide a link below. And you can give the top tracks of 2017 a listen. Thanks for watching and have a good day.